This is the final video of the final layer that we will talk about. In this video, we will look at connectors, and from it we will derive a schema that one can use to discuss hardware. We won't delve deep into it though before we look at a more global element of communications, the use of undersea cables. Our intention in this final video is to talk about hardware. But before we go there, let's just quickly talk about an idea. And the idea is often expressed as the network is the computer. This is an old idea. It is an idea that has seen many incarnations. And one of the incarnations was developed in the early 90s. The idea was to build computers without disks. So here you have an example of such a computer. It's the manufacturers, big brand manufacturers that built them. And at the time that it was built, it would have be deemed a very small computer relative for the power that it provided. And the power that it provided came from the fact that it was diskless. You plug this into the network, and then everything would be loaded from the network, everything that would normally come from the disk. So the operating system image, when it booted, would come from the network, and everything else would come from the network. Obviously, this would seem attractive for producers or for IT management, rather, because they had to maintain a single image. There was no notion of upgrading all the personal computers. You could simply upgrade the one personal computer or the one image, and it would get its input from there. Another example from the same time is this lovely Java station produced by Sun. It's got a very powerful processor, lots of RAM, but no built-in disk. Everything that it needed was supposed to come from the network. One of the interesting things to look at is the series of ports that are available, that are provided in the back of these machines. So as an example here, there you have your connector to the screen. The mouse and the keyboard would have had their own connectors. In fact, that was a serial connector. That's the mouse and the keyboard. And then also connectors for sound. The RJ45 connector, the all-important one, that would connect it to the network. Or if you want to be pedantic, the 8P8C connector, which is slightly different from RJ45, but everyone calls these RJ45s. And then there's the serial connector. And I want to say quite a bit about that. On the other computer that we just looked at, you have a similar array of ports. There's your screen connector. There's your parallel connector for the printer. Parallel in the sense that if it sent a character to the printer to be printed, all the bits that made up that character would be sent in parallel next to one another. That is obviously in contrast to the serial connector that would have sent out the characters or the bits one after the other in a serial fashion. Again, RJ45 or 8P8C connector up there. And again, my emphasis is on the serial connector that we're going to talk about now. If you look at a more modern computer, then very often you will see that there are hardly any connectors. There's a USB-C connector, also a sound jack, and at the other end we also have a USB-C connector and that's it. Those are the only external connectors, apart obviously from Bluetooth and all the other wireless options that exist to connect this. The serial connection that I want to talk about in a bit more detail is the notion of RS232C. That is an abbreviation for recommended standard number 232 revision C. This went up to revision D in the old days, but nobody cared about revision D. The reason why I want to talk about it is not because it is something that one should really know about nowadays. It's also something that has come and gone, and you hardly ever encounter it in the current world. But one of the nice things that you would have seen if you ever studied this standard was that it made a distinction between four aspects. And these four aspects form a very nice schema to think about whenever you think about hardware connections. The first point that it raised was that a standard has to say something about the functional aspects of the connector. Functional refers to the function of every wire if you are talking about a wired connector. One of the interesting things about the RS232 standard, which was a serial standard, is that it used 25 wires between endpoints. That is ridiculous. If you want to carry one bit in serial across, you only need a handful of wires. About 4 or 5 or 6 will do it. You don't need 25. But RS323 provided 25 or required 25 wires to run between endpoints. It also had this rather interesting notion that you would connect so-called data terminal equipment to data communications equipment. And you wanted a straight-through connection, so pin 1 on the one end may have been transmit, and then pin 1 on the other end would be receive. To see the actual specifications or assignments of pins, you can look at the screen, the picture that is displayed on the screen right now. Not necessarily to try and memorize that. I don't know if there's anyone in the world who knows those 25 connections by heart. The second aspect of RS232 that was to be specified was the mechanical aspects. Mechanical, what does the plug or the connector look like? The original standard said that you needed to use a so-called DB25 connector. It looks like the letter capital D if you look at it from the side, and it has 25 pins in it. And that is what was supposed to be used. We'll touch on this again in a more modern context in a moment or two. The next aspect that it said that should be defined was the electronics or electrical aspects. The electrical aspects refer to what the various voltages would mean. Perhaps also what the impedance and the currents and everything else that you may encounter in an electric context may mean. Finally, they spoke about the procedural. The procedural specification. Now, the procedural specification refers to what happens when. Here, as a typical example, a computer that wanted to talk to a modem would first of all raise the RTS line, the request to send line, and then the modem would raise the clear to send line, CTS. In that way, there was a sort of a handshaking going on before the actual content, the actual serial stream of bits would be transmitted. So the procedural aspect talks about what happens when to get this to work. Just as an aside, what we are seeing on more modern equipment, for example, the USB-C ports that I showed you just now, USB-C really talks about mechanical aspects of it. What does the connector look like? What are the electrical levels? How many milliamperes can you draw through that connector? And now we have to begin to say, are we talking about USB 3.0, USB 3.1, USB 3.2, and names such as Thunderbolt gets thrown in there. And you also have to know whether the port is actually a Thunderbolt port. You can't see it because they all look the same. It's all mechanically the same. But the electronics differ. I'll leave it up to you to look at the functional aspects. Are the wires the same in all USB-C connectors or not? The serial port used 25 pins to connect. Then it was realized that 25 pins were just too much and was reduced to the DB9 standard that we encountered earlier, where only 9 pins were used for the connector. In a more modern incarnation, here is a serial port that uses an RJ45 or 8P8C plug to connect. So that even though it looks like an Ethernet conductor, is actually an old style RS232C port, but one where they forgot about the mechanical aspects and they redefined it. This particular plug goes to a USB, this is a USB 2 plug, and it converts the RS232 signals to USB 2 signals. This particular one is used in an inverter where you plug it into the inverter and then you plug the USB port into your personal computer, and the inverter, an industrial type of equipment, where you would still expect to find old-style serial ports, can now talk to a modern computer that uses a much more current standard, although even as you saw on the laptop that I've just shown you, these ports are also disappearing from it. One of the examples where you can still use the schema that we've shown you here to talk about connections is optical fiber. If you've not done it yet, go and just Google optical fiber connector, and you'll see that a plethora of such connectors are being used. Clearly, if you are talking about optical fiber, then the functional aspects become much less, because optical fiber is basically one signal that can be transmitted in one direction. So a typical connection would use 2 fibers. The mechanics, the plugs, we just talked about those. The electronic aspects will clearly be changed by the light aspects. What sort of a light do you use? What wavelengths of that light? And the procedural aspects, how do you turn the light on and off so that you can communicate in an efficient manner? In the same way, if we think about wireless communication, we can again use exactly the same scheme. So even though this is an old way, an old schema to look at connectors, it is useful. You just have to think a little bit broader. These interfaces obviously operate at a very local level. They are right at the back of your computer or at the side of your laptop or somewhere on your router or modem. Such diagrams of interfaces and the accompanying mechanical and functional and procedural and electrical specifications are pretty common. In fact, a lot of these issues are so common that they were the topic of a recent XKCD comic. In that comic, Randall Munroe gives us a picture of such an interface, but with the strangest labels and functional annotations. I urge you to go and look at it in detail. It is at xkcd.com. If xkcd doesn't make sense to you, then it's useful to go to explainxkcd.com. And in fact, I urge you to do so, because when you go through the explanation of this comic, you are bound to learn quite a number of things from that explanation. Well, our discussion of interfaces thus far focused on connections that are very local, on the back of your machine or at the side of your laptop or somewhere in your router. We also have to look at the bigger picture. We have to talk about how messages can be sent between countries or even between continents. We've already discussed satellites that can be used for that purpose, but the bulk of such traffic flows via undersea cables. And we will soon take a look at what the current situation is in terms of undersea cables for Southern Africa. However, it's good to think about where it all began. And it probably began with the story of Samuel Morse, who invented Morse code, and then telegraph machines were erected, cables were erected over land, and then cables were erected in shallower waters in the Mediterranean Ocean and so on. But the Holy Grail was to cross the Atlantic. And in 1857, that attempt began. Here I have a newspaper story that tells you about the details of that particular attempt. It is dated 22nd of August, 1857. One of the interesting facts is that this process actually began on the 5th of August. If you think about the current news cycle, where you look at things that happened today or will happen today or happened yesterday, it took about, over 2 weeks to make the newspaper. The attempt in 1857 didn't work because the cable broke, in fact, twice. Interesting to note that this cable was so heavy that they required 2 ships to carry it. The cable consisted of 7 copper wires inserted in a form of latex, and that was wrapped in hemmed that was saturated with tar, and that was inserted in a sheath that consisted of iron. But the problem was that the cable broke soon after they began laying it, and not long after that it broke again, and they gave up for 1857. In 1858 they tried again, failed again, but in 1858 they tried yet again, and this time they managed to get it to work. The moment they got it to work, they sent a couple of test messages across, and then they were ready for the big opening. And during the big opening, Queen Victoria sent a message to the US President at the time, James Buchanan. Queen Victoria's message read, "To the President of the United States, Washington. The Queen desires to congratulate the President upon the successful completion of this great international work in which the Queen has taken the deepest interest. The Queen is convinced that the President will join with her in fervently hoping that the electric cable which now connects Great Britain with the United States will prove an additional link between the nations whose friendship is founded upon their common interest and reciprocal esteem. The Queen has much pleasure in thus communicating with the President and renewing to him her wishes for the prosperity of the United States." President James Buchanan replied from Washington City, dated August 16, 1858, "To Her Majesty Victoria, the Queen of Great Britain. The President cordially reciprocates the congratulations of Her Majesty the Queen on the success of the great international enterprise accomplished by the science, skill, and indomitable energy of the two countries. It is a triumph more glorious because far more useful to mankind than was ever won by conqueror on the field of battle. May the Atlantic Telegraph, under the blessing of heaven, prove to be a bond of perpetual peace and friendship between the kindred nations, and an instrument destined by divine providence to diffuse religion, civilization, liberty, and law throughout the world. In this view, will not all nations of Christendom spontaneously unite in the declaration that it shall be forever neutral, and that its communications shall be held sacred in passing to their places of destination, even in the midst of hostilities. Signed, James Buchanan. The problem with that message was that the highest speed that they could achieve on the cable was one character every 2 minutes and a little bit. They were using Morse code to transmit it, and it took them over 17 hours to transmit the message from President James Buchanan to Queen Victoria. Still, it was much faster than the typical 6 to 10 days it would previously have taken to send such a message, because someone would have to travel to the other country. But at 2 minutes per character, communication was rather slow. In fact, they attempted to increase the speed, and to do that they increased the voltage, and as they increased the voltage, the cable broke again.
Early telegraph wires tended to follow railway lines, which were also expanding fast across land. But how could you overcome the barrier of the sea? The first attempt was made in 1850, when an international submarine telegraphic link was constructed on the orders of a British entrepreneur, John Watkins Brett. It joined Dover in England and Cap Gris-Nez in France. It was a simple, poorly protected copper wire, and a stronger cable replaced it the following year. Stock prices were exchanged between Paris and London. The Atlantic Ocean presented a far bigger challenge. Nevertheless, American businessman Cyrus W. Field organized the laying of a telegraph cable beneath the Atlantic in 1858. Britain's Queen Victoria and US President James Buchanan used it to exchange congratulatory telegrams. However, the line failed after a few weeks. Supported by Field, a transatlantic cable was successfully laid in 1866. It was carried aboard what was then the biggest ship in the world, Great Eastern, designed by a British engineer, Isambard Kingdom Brunel. Submarine telegraph cables also reached India, China and Japan in 1870, Australia in 1871 and South America in 1874. By 1880, more than 150,000 kilometers of cable had been laid worldwide.
For many years, through many possibilities, Steve Song has published a map of undersea cables in the African region. He is kind enough to share that map with us through a Creative Commons license, and I urge you to visit the URL provided to find the most recent version of the map rather than look at the version that we are talking about here. Presumably it is obvious, but the various lines represent the various undersea cables in the South African region. The different colors represent different cables, and the thickness or the width of every line depicts the capacity of that cable. For those of us who've been using the internet for a long time, the most interesting part of this picture may be the SAT3 cable. That is a thin line sitting there going up north, which for many years was the only connection that South Africa had via an undersea cable with the outside world. Yes, the SAT2 cable also existed at some point, but the SAT2 cable was only used for international telephone calls, not for data communications. You can also see the safe cable here, more or less the same capacity, going out towards the east. One of the interesting cables that we should look at is the CCOM cable. It is depicted in red here. Visit Maputo there, and then goes up along the east coast of Africa to get a better understanding of what installing such a cable entails. Let's look at a couple of excerpts from a CCOM promotional video from 2009.
3 ships were deployed to lay the CCOM cable. One ship began in Egypt and headed south. A second started in India and worked westward. The third and largest ship, the Tycho Resolute, began in South Africa and traveled north.
Tycho Resolute, which is carrying the largest load for us, is just an amazing vessel. Ultimately, it's going to deliver one of the most important pieces of infrastructure for East Africa.
The Resolute is a technological marvel. It uses a dynamic positioning system to ensure that the cable is laid exactly where it should be. But despite all of the computers on board, much of the work is still done by hand. It's a big job, but the crew is up to the task. The ship's hold stores thousands of kilometers of cable, which is paid out as the Resolute travels north. Meanwhile, smaller branch cables are laid from terminal stations on the coast, extending to approximately 3 kilometers offshore. The Resolute must stop and pick up the branch cables off the seafloor in order to connect them to the main cable. The Resolute uses a grappling hook to pick up the branch cable and bring it on board. Once the branch cable is recovered, it's brought into the ship's laboratory, where engineers splice it to the main cable.
Now, when you talk about splicing fiber optics, you're talking about an exact science. There can be no degradation in the signal when they're connecting these 2 pieces of glass, these 2 pieces of fiber optic. The fibers cannot even be a nanometer out of place. To do this on a moving vessel is impossible. So you have to keep the Tycho Resolute completely stationary while the engineers are doing the splicing work.
The crew of the Resolute carefully lowers the newly spliced cable into the sea. This process of joining the cables proceeds until there is one continuous system that's integrated with the global fiber network.
I think it's fairly common knowledge that CCOM lands at Ntinzini in the Durban region. On the west coast, SAT3 lands at Melkbosstrand, very near Cape Town, and then just a little bit to the north, the other cable that is of interest to us, the Western African Cable System, WACS, departs. It's the one that is listed in purple there, and you can see that it lands at Swakopmund. It lands in Angola, at Tsangano, it lands in the DRC at Mwanda, and so I'm not going to list them all, but the point is that this cable is one that lands at quite a number of West African ports, or ports on the western side of Africa. Going around the bend there, and up north towards Europe until it also arrives in London. There is another cable on this picture that we should keep an eye on. It's this green one. It is listed here in the legend, Link, and it is supposed to be operational in the 4th quarter of 2020. Will be interesting to visit their website to see what is going on. You can also see this dark blue one, greyish one that is coming there. It seems from Esterfontein, but maybe Melkbosstrand, Equiano, which is supposed to be active in the fourth quarter of 2021. So again, one that is worth going to the website to see exactly what the progress is and what happens. Just following those, we can see that both of those cables go towards Europe, the one landing in Portugal and the other one going straight to London. Yet another cable that I've been watching is SAX. It's that yellow-brownish one there. It's here, listed here, and it comes from Fortaleza in Brazil. Some initial plans, and it may still be the plan, was or is to extend that cable also to South Africa. Whether that's going to happen or not, we'll have to wait and see, but this will provide us with a link to another continent rather than Europe, part obviously from SEACOM that goes to India. Most people are impressed by the speeds of these cables. If you look at the SAT3 cable, which, as I said, at some point was our only connection to the outside world, and then the Western African cable system running at 14.5 terabits. It's not clear from what I see here whether that is the available capacity or the capacity that is actually being deployed right now. When you look at these cable speeds, you should just double check what you are looking at, where you are looking at the eventual speed at which the cable can run or the bandwidth that has been made available. So at this point then, more or less 15 terabits per second that we are getting out of those two cables potentially. And very soon, in addition to that 15, we may have another 72 added, and then suddenly another 100 added. So you can see the speed increases here. It's almost a doubling in general when you get these new cables in place. On the eastern side of Africa, it's basically SEACOM that is active and of interest to us right now. So 12 terabits, we've seen the more or less 15 terabits on the western side of Africa. So that gives us 27 terabits or so connectivity right now, but set to increase very, very soon. Keep your eye on this one that's happening. Also keep your eyes on what's going on there. Perhaps the bottom line is that we have quite good connectivity in South Africa compared to many other African countries. Also, given the fact that cables are being installed or planned for the future, means that we will have increasing access. However, one of the things for you to think about is that there are large parts of Africa that are nowhere near the coast and that do not necessarily have good internal networks. In fact, there are a couple of countries there that have almost no connectivity. Expensive satellite communication is the only option for a number of them. And when we are simply surfing the net or doing something that has become everyday activities to us, we should remember that not everyone in the world is that fortunate. There is so much that remains to be said. Do you people still know what concentrators are? Do they need to know? Do people still know why this type of modem is so useful? Does this give them a hint? Do they still need to know what modems are? Do they still know why the icons in their phones to make a telephone call look like this. So much that we haven't had time to discuss. We haven't talked about carrier-grade connections. Also haven't talked about some of the really exciting new developments. The Internet of Things, home automation, the associated protocols of Zigbee and Z-Wave. Those are all things that are worth looking into right now. And the field keeps on growing. We simply won't have time in any such course to look at everything that needs to be discussed. One parting thought is the following. In this module, we've talked about the technicalities of networks, protocols, the operation of software, the role that hardware plays. But there is another dimension on it as well, and that is the extent to which networks have changed our lives. Previously, as we saw in the example of the telegraph, you had to sail to a different country to get a message there. Now we can get it there in seconds. In general, that is very good. But there's also the aspect of it that we can never leave our work alone, that we can never get away from it all. And in that way, it has impacted on our lives in ways in which we never foresaw, and in ways that we should think about carefully if we want to stay sane in a world that keeps on going faster. As a parting thought, this whole module was constructed around the ISO model. Randall Munro from XKCD fame has also drawn a comic, a cartoon strip, about the ISO model. Google it, read the explanation, and enjoy.
Music